Part C is the difficult part of this question. Part A and B we've seen before in questions in previous videos in this series. So what I'll do is I'll go through Part A quite quickly, and then for Part B, I'll show you a different method to solving these kinds of equations, which you may prefer. Right, so Part A, we're trying to find the coordinates of P. P is the vertex of this graph. The graph has this equation here, so it's a transform modulus function. What are the transformations that have happened to it? So we're starting with a regular modulus x graph, which let's say looks like this. That is then being shifted to the left by 4 places. So it'll look something like this. This coordinate here will then be minus 4, 0. Then the whole thing gets stretched vertically by scale factor 2. That doesn't affect this coordinate, but makes everything steeper. So it might look like that. And then the final part is the minus 5, which shifts everything down 5 places. So this vertex, which was at minus 4, 0, now drops down or sinks down to here and will become minus 4, minus 5. That is our answer to Part A. And then for Part B, so we're solving this equation. 3x plus 40 is equal to 2 times the modulus of x plus 4 minus 5. Right, so in previous videos, I showed you a graphical way of solving this. So what I'm going to do now is I'm going to solve it in an algebraic way. So this does not involve any graphs. The first thing to do is to rearrange this to make the modulus part of this function the subject, so the x plus 4. So we'll have to add 5 to the left-hand side. That makes it 3x plus 45, and then divide it by 2. So I'll do that all in one step. This becomes the modulus of x plus 4 is equal to 3x plus 45 all divided by 2. So if the modulus of x plus 4 is equal to what we have over here, that means that the x plus 4, so what's inside the modulus symbol, can be equal to plus or minus 3x plus 45 over 2. So very quickly, I'll give you a similar example. If you have modulus of x is equal to 5, that means x can be either equal to plus or minus 5. When you do the modulus of either of these things, you end up with 5. So we can apply that same logic to this. We can say that x plus 4 is plus or minus what we have over here. So I'll write that in 2 separate equations, and I'll actually do that in 2 different colors as well. So let's start with the positive one. I'll call that equation 1. And then x plus 4 is equal to the negative of 3x plus 45 over 2. Let's call that equation 2. Okay, let's solve these 2 things now. We'll start with equation 1, the purple one, times everything by 2. We get 2x plus 8 is equal to 3x plus 45. And if we rearrange this, we end up with x is equal to minus 37. And then for the blue equation, times everything by 2 again. 2x plus 8 is equal to minus 3x minus 45. That's equation 2. I've just times this whole thing by the minus sign. Rearrange. 5x is equal to minus 53, and then we get x is equal to minus 53 over 5. Right, so we have 2 solutions, this one and this one. So that's pretty straightforward. There is one check that we have to make sure that we always do, and that's to put these 2 solutions back into our equation to see if they work. As we're applying the modulus symbol to x plus 4, that means this term must be positive. If the modulus of x plus 4 is equal to what we have on the right-hand side here, then 3x plus 45 over 2 must also be positive. So what we can do to test if our values are correct is put the 2 of them, the x equals minus 37 and the x equals minus 53 over 5, into the right-hand side of the equation that we have over here. So replace the x with those 2 values. Check and see if this fraction then becomes positive or negative. If it's positive, that means the x value that we put in is a solution to this equation. If this expression here is negative, that means the x value that we put in is not a solution, because the modulus of x plus 4 can't equal to a negative number. So let's start with the minus 37. So we're doing 3 lots of x is minus 37, plus 45 over 2. That gives us minus 33, which is negative. So basically, when we use that minus 37, the solution that we got, this part of the equation here becomes negative, and modulus of x plus 4 can't equal something negative. Therefore, we know it can't be equal to minus 37. That can't be our solution. And we'll just quickly try the x is equal to minus 53 over 5 as well. So just replace the minus 37 in the equation above with minus 53 over 5. And this gives us 33 over 5, which is positive. That's exactly what we want. Therefore, this must be our solution. Our final answer must then be x is equal to minus 53 over 5. And on to part C, onto the difficult part of this question. A line L has equation y is equal to ax, where a is a constant. Given that L intersects the modulus function at least once, find the range of possible values of a, giving your answer in set notation. Right, okay, so y is equal to ax is a straight line that goes through the origin. That's intersecting the modulus function that we have above at least once. So for instance, our line could look like this or like this. There's loads of options, there's loads of variations of lines that go through the origin and intersect the modulus function. So before we start properly sketching on this graph to figure out the range of gradients, let's work out the equations of the two lines that make up the modulus function. So we know that our modulus function is this, just copying it out from the question. And if we make what's inside the modulus function positive and then negative, that will give us the equations of the two lines that make up that modulus function. So here's the positive version and then the negative version. So two lots of minus x minus 4 minus 5. Expanding these two things out, 2x plus 8 minus 5 would be plus 3. And this one, minus 2x minus 8 minus 5 minus 13. So two lines, one has a positive gradient, one has a negative gradient. We can then easily match it up to the two lines in our modulus function. The positive one would be 2x plus 3. So let's say that's the purple line. And then let's say the blue line is minus 2x minus 13. Okay, so now let's think about y is equal to ax, what different positions it could possibly take, such that it intersects this modulus function at least once. So if I were to draw a line which is completely parallel to the purple line, so something like this, that line will never cross the modulus function. It will never hit the blue line, and because it's parallel to the purple line, it will never hit that either. If the line were just the slightest bit steeper, it will eventually cross this purple line. And if you continue to make it steeper and steeper, in other words, making a, the gradient of this line, bigger and bigger until it approaches infinity, we see that it continues to cross that purple line. So we know that the gradient of our purple line is 2. The gradient of this line, which is a, must therefore be bigger, but not equal to, it must be bigger than 2. So that's one condition for a. So a must be bigger than 2. That's not the only interval that we need to consider. If we go back to our graph, if we were to make our line shallower, eventually it gets to a point where it crosses through point P. So make our line shallower, eventually it crosses through point P, it touches our modulus function. Now we start to have intersections and therefore solutions between y is equal to ax and the modulus function. What happens if you continue to decrease the gradient of that function? So if you make the gradient close to 0, so you keep decreasing it, you still see that it crosses the modulus function. So shallower gradient, eventually you get to a point where the gradient is then negative, and it still crosses the modulus function. And as the gradient of that line approaches negative infinity, again, we still see that it's crossing the modulus function. So basically, if the gradient of this line is less than the gradient of the line that crosses through point P, so all of those lines that I previously drew had a gradient less than the gradient of the line that crossed through the origin and point P, then it will hit this modulus function. So we then need to work out the gradient of this line that goes through point P and the origin. Point P is minus 4 minus 5. So if we consider change in y over change in x, the point we're considering is minus 4 minus 5. So 0 minus minus 5 divided by 0 minus minus 4. The zeros come from the origin. I'm finding the gradient between this point here and 0, 0. This is 5 over 4. So a must be bigger than 2. It must also be less than or equal to 5 over 4. Why can it also be equal to? Because if it were equal to, as we've drawn in this diagram over here, if the gradient is equal to 5/4, it crosses through this point P and therefore intersects the modulus function at least once. Final step is just to get this in set notation. So these two inequalities do not overlap. If I just draw a very quick number line for that, 2 is over here somewhere, 5/4 is over here somewhere, 5/4 is 1.125, or 1.25, sorry. Those two inequalities do not overlap, and therefore we cannot combine this to make one single inequality, rather we have it as two separate ones. So set notation will then be this. A is a set of values such that it is less than or equal to 5/4, or more than 2, squiggly brackets, and then you put the union symbol or the or symbol in between those two things. The or symbol means that it's both of these regions, not simultaneously, because obviously they don't overlap, but our answer contains both of these two regions. It's this region or this region. The and symbol or the intersection symbol means the overlap of these two regions. These two regions do not overlap, therefore we cannot use that and symbol. So this will be our final answer.